Hi, welcome to the pre-calculus lecture series. This is chapter 4. We are talking about the exponential and the logarithm function. So this video is covered section 4.2. We're going to talk about the natural exponential functions. So the natural exponential function, in fact, this is one of the most popular exponential function we use in the many different type of the math topics here. Okay, so this will be a pretty short video because we're just going to do the introductions and do a couple examples to show you what is the natural exponential function. Okay, so let's go ahead to go to our lecture notes here. Okay, so what is the natural exponential functions here? Okay, so the natural exponential function, so we talk about the exponential function, right? So in general, we define it in the first video, we say the f of x is the ax, right? A is greater than 0. And so the a is the base. Now, if we have a special basis here, right? So the natural exponential function, that means the special basis here. So this is a function we call that this is f of x, ex is here. Okay, so the e is a kind of the irrational number, like similar like the pi, and the e is 2.7128 and dots, right? So e is a kind of the irrational number, and so this is, so when the base of the exponential function is e, we call this is a natural exponential function because the e, we call this is a natural numbers here. Okay, so this is the natural numbers here, and like in fact in the math, especially like in the calculus, a lot of time when they talk about the exponential function, in general, they are referred to the EX functions here because, like I said, this is the most popular one among all the exponential functions. So that's what, but like I said in here, when the people talk exponential, most likely they are referred to the basis E. So what is this E? The E, this is a number, and this number is kind of like this is the definition for the numbers here. So that means when n will go to the infinity, then to the 1 plus 1 over n to the nth power. And this number was first kind of investigated by the mathematician called Bernoulli. And then remember we talk about, we talk about the compound interest, like in the previous sections, right? So we talk about compound interest, like 1 plus r to the n's, right? So in fact, Bernoulli, he's working on the compound interest. So he was said, if I can compound infinity number of the times, so what that will be? So that was the original thinking about this E numbers here. Okay, so also like we talked about before, so like we say, the large the base E, the more steep the increase, right? So like in here, if you have like, if this is like the 2 to the x, so I know the 3 to the x is going to be here, right? Because the 3 to the x is more steep. So the e to the x, because e is 2.71 something, so this will be the e to the x. So right between the 2x and the ex is here, right? Okay, so like we talk about the so we say the natural, so this is how the natural number. So this is, if you put it into the calculator to 7, so it will be 2.7128 or something like that. Okay, and now let's take a look here. The one of the applications here, in here they said is the continuous compounding here. Okay, so remember, right, this number was first investigated by the guy named Bernoulli, right? By the guy Bernoulli. In fact, Bernoulli was calculating the interest. So that's why he said, how about if I compounding continuously? So we did an example in the previous video. We said we're compounding like every day. Now, how about if you want to compounding every minutes, every seconds? Then what is that? So in fact, we find these formulas here. So he derived this formula. So if you compounding continuously, then this will be, we call this a PERT. So sometimes we call this a PERT. Okay, so the P still, this is the principal, and R is annual rate, and the T is what? The number of the years. Okay, so the similar one, okay, so this is how do we calculate the compound interest, the total amount, right? But the same concept we can apply to, we call this exponential decay or exponential growth, right? Okay, so what is, so it's exactly the same one. So the formulas here, they will say this is the P, and this is like the P0 E R T here, right? So it's not the interest anymore, but it's the same formulas here. So in here, this is what we call this P0s here, right? So the P0 is similar like the principal. This will be what? That is your initial population value, right? What initial value that, so if you don't want to use a population, so you say this is the initial values here. And then the R is the rate, right? So the R is the rate. So if if you have a negative, that means I'm going for the exponential decay. And if you're positive, that means what? That means I have the exponential growth here. And then T is the time, right? So of course in here, the T and the rate, they have to match. So if the rate is hourly rate, then the T has to be every hours, right? So like this is the model, like in today's, we have because of the pandemic, right? We have a lot like the estimation graphs, those things here. So like that's why, you have like, for example, for certain community, you start with initial how many effective people, then you put this model, then you figure what is the rate to growth, right? That's why we say the pandemic, the effective people, the growth is like exponential growth. That's what is here. So if let's say every 2 days, I'm going to double it, then the days, the times here will be every 2 days here, right? And also like the like the latest study, they show the coronaviruses, if you left the coronavirus on the hard surface, then the latest report, they say the half-life of the coronavirus is 6 hours. What's that mean? That means, the P0, if initial, you have 100 viruses there, then after 6 hours, then what is the P is the end product, right? So that means you only have 50, the virus. That's what we call it, the half-lives, right? So the R here, the half-life will be the negative one half because you decrease half every time here, right? So this is so basically this formula you can apply to the interest, and also you can apply to a lot in the real life. So for example, decays here, also like we talk about, for example, like the radiations, right? So if you have some radiation source, then if you put a radiation source there, then after time, then the radiation will gradually decay, right? So that's how do we use this model to estimate. So if we say if it decayed at 10 years will decay like 10%, how much is after 100 years, how much radiation is still left here, right? So it's very, very unpopular function and the model. So that's what is this section about. So, you know, later when you try to do some work problems, you will see it's all this related to those exponential growth or exponential decays here. Okay, so let's take a look. The first problem here. So let's say infectious disease begin to spread in a small city population, 10,000. Okay, so the P initial, right? So this is my P initials here, right? It's 10,000 here. After 10 days, the number of the people who have succumbed to the virus is modeled by this function. In fact, this is what we call the logistic functions, and a lot of the current study was modeled by these functions here. So the first ones here, they ask you, say, how many infected people are in there initially, right? So because this is the populations here, the whole populations here is 10,000, right? So when they initially, that means t equal to 0, so you will have this is 10,000 here. So this is 5 plus 1, 2, 4, 5, and e to the zeros here, right? So e to the 0 is 1, right? So this one's here will be what? This will be 10,000. So it's 5 plus 1, 2, 4, 5, right? Okay, so now you will get the numbers here is 8. Okay, so that means initially, if you only have 8 people at the beginning to start with, is 8 here. Okay, so then they say find the number of infected people after 1 day, 2 days, and 5 days here. Okay, so here, this rate, they say, is t days, right? So that means t is modeled by the days. So it's okay here. So let's take a look at the second ones here. So we can say day. So 1 day, 2 days, and 3 days, right? So you just 1 day, you just put this will be 10,000. Then this is 5 plus 1, 2, 4, 5 to the e to the ones, right? Negative 0.97 times ones, right? Then you put it into your calculator, you will get this ones here is 21. And then the next day you do the same thing. So you just put a negative 0.97 times 2, right? And then add back to here, you will get 54 people get infected. Then 5 days later you put this is 5, so you will get 678. Wow. You see here, right? So this is the affected people see here. So that's why we call this exponential growth. It's grow very fast. It's very steep growth here, right? So it's 2154 and this, 678 here, okay? And so that's what we call this, how to use the exponent, the natural number E, try to do the estimations here. Okay, so now the next ones here, this is a compound interest. So let's say I want to find the money after 3 years. If $1,000 initially invested and invested at the rate 12%, compounding what? Compounding continuously. Okay, so now I can say here, so A is PERT, right? So this is my principal. So this is 1,000 E. R is here, right? So it's a point of what? 0.12. How many years? It's 3 years here. So now if you put it into the calculator, and you will get it is 1433.33. Okay, so that's a lot after 3 years if it's compound continuously. So you get about $433 interest here. Okay, so that's it for this section. It's very simple sections, but it's a lot of applications. The idea is easy. So the base is here. Instead of any number 8, this is the base, right? So this is the natural numbers here. So this is what we call this natural numbers. And it's, like I said, also in the most of the math topic, when you talk about the exponential function, most likely they reference to the e to the x. Of course, this is the general definitions, right? This is the general definitions. And that's why for here, we call this a natural exponential function. But like I said, the EX one, the natural exponential function, has way more applications. So that's why typical when we talk about it, we talk about it is the EX functions. Okay, that's it. Like I said, this is a very short video, and but the application is tremendous. Okay, okay, that's it. Nice to talk to you. And then our next topic, we're going to start to take a look at the logarithm functions here. Okay, all right. Nice talking to you. Have a good day, and bye.